Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Aminul Solihin. In this video, I would like to explain about revolutions and rationality in philosophy of science and Kuhn's revolutionary history of science. The first is revolution and rationality in philosophy of science. The scientific method is supposed to be rational and give us objective knowledge about the world, meaning that it is not the product of individual desires and that is worthy of belief by all people, regardless of their beliefs and values. For example, if it is an objective fact that smoking leads to cancer, then it is believed equally by all people if these people are to be rational. Previously, Hume argued that science was inductive and irrational. Popper stated that science was non-inductive and rational, and Carnap stated that science was inductive and rational. However, in the 1960s, there was a crisis of realism and rationality in the philosophy of science, which has not been overcome and resolved. Many people question the rationality and objectivity of scientific knowledge, especially because ideas first appeared in the work of historian and philosopher of science named Thomas Kuhn. In contrast to Hume, Popper, and Carnap, Kuhn argues that science is non-inductive and non-rational. The next is Kuhn's revolutionary history of science. Kuhn, in his book The Structure of Scientific Revolution, 1962, offered a radically different way of thinking about scientific methodology and knowledge, and changed the practice of the history of science. His philosophy of science has led to the spread of world paradigm, in which it is a set of accepted belief, practice, and theories that guide scientific research within a particular field for a certain period. Furthermore, Kuhn argued that scientific development is not a continuous, cumulative process as previously thought, but rather occurs in distinct phases.
Thomas Kuhn, he wrote a book. It's a guy who invented the term paradigm shift. Like in the 60s, he wrote a book like Scientific Evolution. And he says, for instance, like when you really want to make a fundamental change, that change has to come from outside the academic world. Because if you are inside the academic world, you have to work with the pieces that are presented to you by your previous generation. In a way, you are puzzle solvers. So a real paradigm shift throughout history always comes from outsiders.
The first is normal science. During this phase, scientists work within a widely accepted paradigm or theoretical framework. They solve puzzles and conduct research that fits within the established paradigm. And the second is anomalies. Anomalies are observations or problems that cannot be explained within the existing paradigm. These anomalies accumulate over time and create tension within the scientific community. And the third is crisis. A crisis occurs when the accumulation of anomalies reaches a breaking point. Scientists become open to new ideas and paradigms as the existing one no longer provides satisfactory answers. And the fourth is scientific revolution. During a scientific revolution, a new paradigm emerges to replace the old one. This shift is often accompanied by a change in fundamental assumptions, theories, and methods. And the last is normal science or new paradigm. After the revolution, a new period of normal science begins, with scientists working within the new paradigm. The process repeats itself with anomalies eventually leading to another crisis and potential revolution. In his theory, Kuhn used the term paradigm shift, in which it refers to fundamental change in the basic concepts and experimental practices of a scientific discipline. It involves a complete transformation in the underlying assumptions, theories, and methodologies that guide a field of knowledge or work. For example, the shift from the belief that the Earth was the center of the universe to the belief that the Sun is the center of the universe. Then the shift from the belief that the earth was flat to the belief that the earth was fair.
I believe his name is Thomas Kuhn. Anyway, he wrote a book on something about scientific revolutions. And he talked about the difference between quote unquote normal science and revolutionary science. And normal science, he just called scientists that are puzzle solvers. You know what I'm saying? Like they just do experiments to say that they did experiments, and they follow the scientific method, and they just reproduce the same stuff all the time. You know what I'm saying? Mm-hmm. Which is a lot of what science is. And I'm not saying that that's bad per se, but that's a lot of what science is. And then he talks about revolutionary science, where, you know, someone had the courage to say, man, I'm seeing something different here, or I'm looking at things differently, and really trying to understand why they might be different than just putting a puzzle together again, because that's not really what science is. And to progress science, you need these periods of revolutionary science where someone has the...
Kuhn argued that if out-of-date beliefs are called to be myths, then myths can be produced by the same sorts of methods and held for the same sort of reasons that now lead to scientific knowledge. Furthermore, Kuhn stated that abandoned beliefs are not unscientific. Hence, the history of science does not consist in the steady accumulation of knowledge, but often involves the wholesale abandonment of past theories.
Paradigms and normal science. Perhaps the most fundamental concept in Kuhn's philosophy is that the scientific paradigm. He doesn't offer us the real definition of this term. So the scientific community in question has to agree upon answers to fundamental questions about, for example, what kinds of things exist in the universe, how they interact with each other and our sense, what techniques are appropriate for answering those questions, what counts as evidence for the theory, what questions are central to the science, what counts as a solution to a problem, what counts as an explanation about a phenomenon, and so on. For the most fundamental concept in Kuhn's philosophy is that the scientific paradigms, thus of paradigms as disciplinary metrics and paradigms as exemplars. For disciplinary metrics is a set of answers to such as questions that are learned by scientists in course of the education that prepares for research. For exemplars, on the other hand, it is the successful parts of science that all beginning scientists learn and that provide them with a model for the future development in their subject. And next, as the example, consider two paradigms of classical or Newtonian physics. It consists of at least the following elements, such as Newtonian chemistry, which is chemical theory according to which the elements may be distinguished by their differing atomic weights, the fluid flow theory of electricity, the calorie theory of heat, the wave optics, the relativistic physics, and then quantum physics. How about normal science? Why is it called normal science? Most science is what Kuhn calls normal science because it is conducted within an established paradigms. It involves elaborating and extending the success of paradigms. Normal science is often said to be a puzzle-solving activity, where the rules for solving puzzle are quite strict and determined by the paradigm. Examples of normal science, including searching for a chemical structure of familiar compounds, mapping the DNA of a particular bacterium, and so on. If a paradigm is successful and seems able to account for the largeness of the phenomena in its domain, tentunya, and if scientists are still able to make progress solving problems and extending its empirical applications, then most scientists will just assume that anomalies that seem intractable will eventually be resolved. They won't give up. One more, they won't give up in the paradigm just because it conflicts with some of the evidence. Next, so there are 2 points about Kuhn's account of this and other scientific revolutions that must be emphasized. Firstly, this is a completely different view of scientific change to the traditional idea of cumulative growth of knowledge, because paradigm or scientific revolutions involve change in scientific theories that is not piecemeal but holistic. In other words, the paradigm doesn't change by parts of it being changed bit by bit, but rather by a wholesale to a new way of thinking about the world. And this usually means a new way of practicing science as well, including new experimental techniques and so on. Secondly, revolutions only happen when a viable new paradigm is available, and also when there happen to be individual scientists who are able to articulate the new picture to their colleagues. I think that's it. Next, presenters.
The Copernican revolution was a significant scientific and philosophical shift from the Ptolemaic geocentric model to the heliocentric model. This transformation, spanning around 150 years from the early 17th century to the end of the 17th century, saw the abandonment of the Earth-centered view in favor of the Sun-centered view. Ultimately, Isaac Newton's theory of gravity provided a unified explanation for planetary motions and related phenomena. The Ptolemaic paradigm had strengths such as aligning with religious beliefs and offering reasonable predictive accuracy for planetary movements. However, it also faced anomalies, which astronomers attempted to address by introducing complex modification like epicycles. Several factors contributed to the Copernican revolution. Copernicus provided an alternative theory, but it was not immediately more accurate than the Ptolemaic model. Individuals like Kepler, Galileo, Descartes, and others played pivotal roles in adopting and developing the Copernican paradigm. This shift wasn't solely based on rational assessment. Individuals had diverse motivations for embracing Copernicanism, including a preference for mathematical simplicity, coherence with worldviews, and personal values. The choice between paradigms wasn't solely driven by compelling rational grounds, according to Thomas Kuhn. The Copernican theory faced challenges and apparent contradictions, such as the absence of observable changes in the size of Venus and arguments against Earth's motion. Advocates of heliocentrism couldn't satisfactorily address these issues initially, raising questions about the rationality of their choices. The characters, beliefs, and values of key figures like Copernicus, Galileo, Kepler, and Descartes influenced their contributions to the revolutions. Copernicus, for instance, was willingly to radically revise the solar system's mathematical description, while Kepler favored mathematical simplicity and had access to detailed astronomical data. Overall, the Copernican revolution serves as an example of how scientific revolutions involve complex interaction between empirical evidence, personal motivations, and social factors as proposed by Kuhn. When explaining how science works, it is natural to immediately invoke a distinction between theory and observation. Scientific theories are supposed to be based on known facts, and the facts are determined by observations. We start by observing the natural world, then we try to systematize those observations, and finally we arrive at the most general principles that govern them. Contrary to what Bacon says, the method we follow cannot be entirely without presuppositions, because when we observe the world, we divide the phenomena into different types before we try to systematize our knowledge of them. So, for example, we begin already having classified some phenomena as the motions of heavenly bodies and others as tides or seasons. Now, according to modern science, it turns out that these phenomena are closely linked. Tides are caused by the motions of the moon, and seasons result from the motions of the earth around the sun. Hence, by treating them as separate phenomena, we may be misled. However, although existing theories guide us in developing new theories and tell us which observations are significant, the distinction between the context of discovery and the context of justification can be invoked to maintain the idea that scientific theories are tested by observations. Many empirist philosophers have drawn a sharp distinction between the observational and the theoretical, and both logical positivist and Popper, at least in his earlier work, assume it. On the other hand, Kuhn was one of those who emphasized what has become known as the theory-laden nature of observation. The idea here is summed up by the philosopher Hansen, who said, "Seeing is not only having of a visual experience, it is also the way in which the visual experience is had." He argued that the visual experience of two observers may be different, even when the images on their retinas are identical. In general, according to Hansen, observation of X is shaped by prior knowledge of X. The idea is that we can see the cube either with the top right square facing us at the front of a cube, or the bottom left square as the front of it. The other picture is a rabbit's head facing left or a duck's head facing right. Kuhn and others use such examples to argue that, in general, what scientists perceive is partly determined by their beliefs. A Copernican looking at the sunset sees the sun stay still and the horizon rise, while a Ptolemaic astronomer sees the horizon stay still as the sun falls behind it. There are other cases where what is observed or regarded as observable seems to be contaminated by theory. According to Galileo's theory of motion, only relative motion is observable, and hence we do not feel the movement of the earth relative to the sun because it isn't moving relative to us.
Next is incommensurability. Incommensurability is a concept borrowed from the mathematics that essentially means lack of common measures. This term gained significance in the work of philosophers like Thomas Kuhn and Paul Feyerabend, who argue that successive scientific theories often cannot be directly compared or measured against each other in a neutral way, because they operate within different paradigms. Kuhn proposed a radical idea that the evidence supporting a particular scientific theory can be influenced by the background paradigm within which it exists. This notion challenges the rational comparison of competing paradigms. Kuhn suggested that there is no superior standard for evaluating theories beyond the consensus of the relevant scientific community. He famously stated that choosing between competing paradigms involved choosing between compatible ways of conducting scientific inquiry, and also to choosing different modes of community life. This perspective has led some to interpret Kuhn's argument as suggesting that scientific progress is not solely driven by objective evidence, but can be influenced by social and psychological factors. It also contributes to the development of the strong program in the sociology of knowledge, which aim to explain scientific theory changes through these social and psychological forces. Kuhn's idea of incommensurability is tied to the concept of theory-laden observation, suggesting that observations are influenced by the background theories of the observer. This means that proponents of different paradigms may not agree on what they observe, making it difficult to compare the merit through experimental tests. Kuhn illustrated his point with the Copernican revolution, where the change in paradigm led to different methods of testing theories and different scientific problems to be addressed. For example, modern science explains how gravity and air resistance affect the flight of an arrow, while Aristotelian science told and explained why the arrow continues in the motion after leaving the bow. Different paradigms may classify things in the world differently, and sometimes questions from older paradigms may not even make sense to those operating within newer ones. Kuhn linked a paradigm shift to crystal switch, where one sees an image as either a duck or a rabbit, and these differences between paradigms are holistic and systematic. Incommensurability also extends to the meaning of scientific terms within different paradigms, a concept known as meaning incommensurability. Kuhn believed that scientific terms derive their meaning from their place within a theory, and therefore the same term in different paradigms can have different meaning. This raises questions about whether proponents of different paradigms are even discussing the same concept or merely using the same word with different meaning. Referent incommensurability goes further, suggesting that different theories about the same concept, like atom or electron, may refer to the entirely different thing. This challenges the notion of scientific progress if understanding the underlying nature of reality and implies that our theories construct the world we perceive. So, in conclusion, about the Kuhn concept of incommensurability highlights the challenge of comparing and evaluating science theories that operate within the different paradigms. So it has sparked discussion about the nature of the science truth, the objectivity of reality, and even the idea that belief itself may be socially constructed. Alright, so let's move to the revolution and rationality. In simple terms, it talks about the big argument in the world of science. The argument is about how we should think about and use science. Some people think science is the only way to know things and that it can explain everything about the world. So they believe that the things like stories and myths from different cultures are not needed because science can tell us everything. They also think that people who don't believe in science are superstitious and not logical. On the other side of the argument, there are people who don't think science is so special. They believe that science is not always better than other way of understanding things, like stories or belief. They also think that sometimes scientists do things that are not very honest or fair, like changing data to fit their idea or not letting others criticize them. But there are some people who say we can believe in science without thinking it's the only way to know things. They also say we can criticize scientists when they don't follow the rules of good science, like being honest and sharing information. So the text also talked about one of famous scientists named Kant, who said that scientists don't always act like they should, and sometimes they stick to their old idea even when there is evidence against them. And also he said that science is not always as logical as we might hope. So, in the other hand, it discussed about whether we should trust scientific completely or if we should be more critical and open-minded to the other way of thinking. It also mentioned that some people believe in science because it helps us to do practical things like building computer, sending rocket to the moon, and while other think that just because a theory works doesn't mean it's always true.